session of today. And the first talk will be given by Michael Niket. The title is Automated Metamodel Augmentation for Seamless Model Evolution, Tracking, and Planning. Please go ahead.
Thank you for the introduction. So this is a very complicated title, so to make it easier, I'm going to illustrate which problems we want to address first. So as an example, I'm going to use a car manufacturer. It doesn't matter which one. So cars of car manufacturer are the major strategic asset of them. So they have some other things, but that's what they sell. What they do not do, if they have a version of a car, they do ad hoc evolution. So they think, okay, what can we introduce? Next week in our model, which we will release. But they have an idea of a long-term goal. So they have these concept cars where they have big ideas where they want to go, and yeah. So that's what mostly management and research decides in such companies. Intermediate evolution happens. So changing requirements or new laws and such things need to lead to such intermediate evolutions and short changes on short notice. But if you do not track this correctly and monitor the intermediate evolution, and if it's matching the actual goal, you may end up in inconsistencies. So that things you did in your short notice steps don't match your long-term goal. And so the development diverges, and you will end up in problems. Either you drop the long-term goals, or you'll have a lot of effort to reestablish consistency. So these large systems are often developed with model-driven software development techniques. So you have models for your car functionality or the construction plan of your car. And what you do, you check and refine it until it goes live at some point in time. And the same applies for your long-term goals. So you have a model for it, and you check and refine it, and also your intermediate steps, you check and refine it until it goes live. And with the planning of your evolution and the planning of your model evolution, you have certain benefits. You can analyze this model that fits your requirements or fulfills certain properties and so on. And moreover, you can monitor the progress. Okay, is my actual evolution matching my plan? So you have artifacts which you can overcome. So this is even more important when you think of conceptual models, such as feature models for software product plans, for instance. Then you have on an abstract level defined functionality of systems. So in a car, this could be the Bluetooth functionality of an infotainment system could be a feature. And what you do there is you have your conceptual model, so your feature model with the Bluetooth, and then you implement the details with some sort of realization assets or code and so on. And this is very important, and then planning is very important because you have your feature model of your future system. So you plan your concepts of your long-term goals. So you have features which you want to have in the end. And in a step-by-step manner, you can implement these functionalities to achieve this long-term goal. So another problem which one of our industry partners has is that different teams work on models. So for instance, the first version of the model is defined by a certain contributor, team 1, and also the long-term goal is defined by them. But in intermediate evolution steps, different teams may perform evolution. And this may lead to problems because these teams may have different focuses on what they want to do, and probably this contributor doesn't know about this long-term goal or what the plans of the mental models of the so this can end up in inconsistencies as well, because you have problems in who is responsible for which parts of a model and who is allowed to change which parts of the model. So coming to our contribution. Right now you have tools and you can create and modify models with it and you can perform evolution on these models. And what you would normally do is you would have a version control system where you would have, for instance, a branch for the long-term goal and a branch for your active development with your intermediate evolution system, which would change then because your long-term goal changes as well and your active development goes also on as well. In the end, you want to merge them. But if they diverge, you have a problem because you will end up in merging conflicts, and this is very costly and error-prone to fix. So what we propose is to introduce an evolution-aware model, which integrates all evolution steps of the model, and also the future planned goals. What you can then do is you can also perform intermediate evolution steps. So we have versions for T1, T0, T1, T6, and you can create also in between a version for T4. Exactly. And overall, overarching goal is to ensure consistency between all these evolution steps, so that each intermediate evolution step will match the planned evolution. So once more disclaimer, we do not solve this in this paper, but this paper is the basis for this. So we are actively working on it, but yeah, this is not it. And an important thing is also that engineers should still use the tools they are used to use. So we do not want them to use different tools. So this has to seamlessly integrate in tool infrastructure. So we did this at one point manually for feature models. So we had the standard feature model editor, and we adapted the editor a little bit, but with such an evolution slider. So this is not part of this one, but just to illustrate what we mean by we use the same tool. So this is the same editor. You can perform the same operations and so on, and you can use the slider to go back and forth in time and see the different states of the model and perform changes on it. Moreover, when talking about different contributors to models, when having access control with state-of-the-art tools, they work on a file basis. So you have a problem when you want to have access control on model element level. So if you have different model files, you can say, okay, this file can only be changed by a certain contributor. And if another contributor wants to change it, you say, okay, you can do it. But if you want to do this on a model level, so certain parts of the model are only restricted to a certain contributor, this is not possible. And this is what we want to do as well. We provide the basis for it. We want to provide a centralized access point to access the evolution around model. And additionally, hide the complexity of this evolution around model, because in the end, we will see it will be large. And it's not very easy to use, but with this centralized access point, it's pretty easy. Exactly. So to be a little bit more concrete, this is adapted from the real-world example. So it is the alarm system of the functional behavior of the alarm system of the car together with the unlocking with the key. So it is modeled with a state machine. So you have a state alarm system on, alarm system off, and if you unlock the car, the alarm system goes to off and potential alarm is deactivated. So in model-driven software development, we would have a Metamodel which describes how you can define a model. So this is similar to grammar for programming languages. And this can be defined, for instance, using such a diagram which is quite similar to a class diagram. So you would have a state machine, and the state machine can have different types of states, and between the states we have transitions. So this is the state at T0, so our initial state. So Also, the LED should be deactivated when unlocking the car. But in an intermediate evolution step, at T2, another team comes into play. A team which is responsible for the remote key, well, which is quite common right now, but at that time it wasn't. What they do is they also change the transition between alarm system on and alarm system off. And say, okay, this transition is also taken if the remote key on the car. But now we have a problem because the planned goal, state changed this transition, and the intermediate state also changed this transition. So we would end up in a merge conflict. So this is quite simple and solvable, but if you imagine larger models, then be quite complex. And another question is, who is allowed to change this transition? Potentially only the alarm system team, but what? We do not. So more details on our contribution. So we have a model matching a meta model. So for instance, the state machines. And what we generate from the original meta model and augmented meta model. So this provides the basis for an evolutionary model. And it potentially stores evolution information on each element of a meta model. Then we provide this centralized access point for evolution, which is called evolution gateway, which hides this complexity. The other point is our adaptive infrastructure. This is important to ensure seamless integration. So this conforms to the original meta model. So well, you can access your evolutionary model via the adaptive infrastructure. Well, as you use to access the original model. But as operations on this model have to be attributed to a certain point in time, we need a clock. We also provide a clock format, so default implementation which is the current system time, but it can be overridden via an extension format. And then tools use the data infrastructure. We implemented everything in the TIPS modeling framework, but the concepts are generally applicable for other meta modeling applications as well. So first point, so how do we generate this augmented meta model? Basis are temporal elements. So a temporal element is pretty simple. It has a point where it starts to be valid and a point where it ends to be valid. And then we provide a set of transformation rules from elements of the original meta model to transform them to the augmented models. So I have 3 examples. There are many more transformation rules, but just to give you an idea how it works. So we have a class. It's really simple. We just let it inherit from the temporal element. So and then it can be valid at some point. Object of that class can be valid at some point in time and stop to be another point. If we have an attribute, we extract this attribute out of the original class and have a temporal attribute. And this class relates to a set of temporal attributes. And this temporal attribute then inherits from the temporal element. So there can be multiple values and even more than the original upper bound for the temporal attribute, of course, because values can change over time. For references between classes, it's quite similar. So we extract the reference to mean own entity, and that it inherit from temporal element, and then we have references between the original class and the temporal reference, and between the temporal reference and the second class. So to illustrate how this looks on code level, so this is what the TIPS modeling framework would generate on a code level. We had an original meta model element with an attribute name. So we had the method get name and the method set name. So this is what was originally there. If we file a transformation rules, we have an evolutionary meta model element which has a reference to a class called evolutionary name. And both inherit from temporal element. And it has now a set of names, or here any products intermediate. Exactly. So second part, how do we realize the evolution gateway? So if we have now the augmented meta we generate this evolution gateway, which matches exactly these methods over here, but with an additional parameter, well, the date for which you want to perform this operation. And then you can access this thing over here by this simple interface. So you do not have to deal with these sets and so on and filter the actual elements which are valid at a certain point in time. That's all generated. And that's also the basis for access control, because here you can say, okay, a certain contributor isn't allowed to change something on element basis. Okay, the last part is the data infrastructure. So if we now have the original metamodel element, the evolution metamodel element, and the evolution gateway, with EMF, what's usually there is a factory, or there is a factory to create actual objects of the model, and which match the metamodel elements. So what we first do is we define for each metamodel class of the original metamodel an adapter element, which has the same method signatures and so on, and so it inherits from. And then we implement an adapter factory, which inherits from the original factory as well. So, and here we override this factory. So each time the user wants to create an original metamodel element, in fact, an adapter element is created, but it's transparent because this adapter element inherits from the original element. So the tool or user wouldn't know at this point. And then we have the same. The methods of the SA exactly match the methods of the evolution gateway, but they do not have a date specified. This date is retrieved from the centralized clock, which, well, yeah, the default is the current system path. And then calls are delegated to the evolution gateway. So here we provide an extended one, so you can override it and implement your own clock. I'm going to show you an example how this may look like. So complex things, how would a method call work? So if the tool or user would call get element name on an adapter element, this would be delegated to the facade. The facade would retrieve the current time of the clock, and then delegate the call together with the date to the evolution gateway. This evolution gateway would retrieve all names from the evolution metamodel element, filter it, and only send back as a result name that is valid at the actual date. So you can access the model or the evolution gateway at each point you want. So you can use also the evolution program model if you want to have control over the evolution program model, so you are not forced to use the adapter infrastructure. But it is there to seamlessly integrate. So we implemented everything as said in the EMF world with a tool called Temporal Regulator 3000 that was done by a student of us. It's pretty nice. So if you have, it's a little bit small, this is a meta model in EMF. And well, this is project structure in Eclipse. And you can just right click it, say convert to temporal meta model. Then there's a dialog where you can select, okay, which elements should be subject to evolution. Then it will be generated and certain statistics will be provided. And a new project will be added, in which the original factory is also overridden. And we have a new meta model. So this is pretty large. Yeah, this is due to the transformation rules, and we extract each attribute and references and so on. Yeah, exactly. So we also evaluated everything. In the first step, we evaluated whether with this method we are able to track and also plan model evolution in one artifact. So an entire model evolution. So we applied it to feature models again. And we had as use case from our industry partner a feature model with 10 versions, and we all imported them as evolution steps within this model. Within this, we also implemented a generic importer for arbitrary models. So we can import versions of arbitrary models into evolution-aware models. Well, it worked, and we verified it and retrieved each evolution step and matched them to the actual versions of the original model, and it worked, yeah. So the second question is whether transparent usage of this evolution-aware model is possible. So what we did there is we had software fault trees and an editor for them. And what we did, we implemented a simple clock, which is not part of the editor. It's additionally, we could have also used the systems clock, but that would be a little bit more complicated than to retrieve a certain model state. So this is a pop-up where you can just put a date in there, again, not part of the editor. And if we set the date to a certain point in time, we could change the software fault trees and also go back in time and see the previous versions in the original editor without adapting the original editor at all. So this was pretty nice. So the third question was whether access control is also possible. So, well, we did it pretty simple. We again used the software fault trees and said, okay, if a fault has a certain name pattern, so it was, if there's critical in its name, it is not allowed to be changed anymore in the future after it was once defined. So using the editor, this ended up, if you want to perform an operation on this fault, well, nothing happened, but we realized simple access control really in a few minutes. So more sophisticated methods can be implemented as well. At least we claim that. Okay, and the last one is whether our method is applicable for large-scale real-world models. And we used, for one, the UML2 meta model of the Eclipse modeling framework, and the meta model of JAMOP, which represents the entire functionality of which can represent Java code as a model with, I think, Java version 1.5, but, well, the entire language. So it took quite a while to generate it, but in the end it worked. Unfortunately, we did not have real-world examples of actual model versions of these models, so this is an open question whether this scales to define such large models. Okay, to sum up my talk, planning model evolution is important. Well, we have industry partner which actually does this, but they manually ensure consistency and track monitor whether actual development matches the long-term goals. So we have augmentation rules to transform arbitrary meta models to evolution-aware meta models, augmented meta models, and we have this entire infrastructure of adapters and evolution gateway to seamlessly access the evolution-aware model. Or if you want to have more fine-grained control, you can use the evolution gateway to adapt information stored in the evolution-aware model. Finally, we have shown that, well, general concepts work for large models and real-world evolution histories as well. So thank you for your attention. If you have any questions, I'm happy to answer them.
We have time for questions. So I was very curious about the scalability thing. So I know you still need to work with that, of course, but could you say something about how much does the size of, in these examples, how much does the size of the model increase?
I can say something about the meta model. I have concrete numbers for it. So for Jamod and the UML2 meta model, so the classes significantly grew, and also the references significantly grew. The attributes, on the other hand, well, slightly reduced. But that's because we can reuse certain classes and so on with our transformation rules, and so we do not have duplication in attributes. Well, for small evolution histories, also the model significantly grows. I do not have a concrete number for it, but with the 10 versions of the feature model, it was slightly larger. But as we only store the difference between each evolution step, we assume that it will be less with increasing evolution history.